Step-by-step exam solution. Okay, physics class, training you to excel. Step-by-step exam solution. Subscribe, like the video, share the link with your friends. Click for notification so that you will be alerted when the next video is available. Please drop a comment so that I can serve you better. Okay, physics class, present steps to exam success. Step 1, pray. Step 2, plan. Step 3, prepare. Step 4, preview. Step 5, perform. These are 5 basic steps to exam success. Okay, physics class, present step-by-step exam solution to radioactivity video number 1. Radioactivity video number 1. In this video, we will be looking at 3 major concepts or topics. Number 1, we'll be looking at the nucleon and proton numbers of a nuclide. Then number 2, we'll be looking at isotopes and isobars. What are they? Why are they important? Number 3, we'll be looking at radioactivity and radioactive radiations. The objective of these presentations are: number 1, define and state examples of nuclides. Number 2, define isotopes and isobars, giving examples of each. Number 3, define radioactivity and state the properties of radioactive radiations. These are our objectives for the presentation. Now let's move straight to the video proper. The nucleon and proton numbers. The animation you are watching now is that of an atom. This animation clearly shows that an atom is made up of 2 parts. The inner core, called the nucleus, and then the outer core, or the outer part, called where you have the electrons. Now, as you can see, the electrons are in orbit around the nucleus. But our focus is not just the entire atom or the electron moving around the nucleus. Our focus in this presentation is the nucleus. The nucleus is the source of nuclear energy. That's why we are concentrating all our attention on the nucleus, because this is the source of nuclear energy. Now, as you can see the nucleus at the center of this atom, you can see 2 major particles you can see there. So it contains 2 particles. And what are those particles? The proton, the one that is almost red in color, and the neutron, the one that is almost blue in color. These are the 2 major particles. I said major particles because right now there are hundreds of particles you can find in the nucleus, but we are looking at the 2 basic particles, the protons and the neutrons. The mass of the whole atom is concentrated at the nucleus. If you look at the whole of this atom, you see that every other part of the atom appears to be empty. The nucleus is just a small part of the atom, and yet the entire mass of the atom is concentrated at the nucleus. The nucleus only occupies a small part of the atom. The nucleus only occupies a small part of the atom. So now, we have seen that, but before we continue, please like the video and then also share the video, and then we're going to continue in our presentation. So we're looking at the first one, the nucleon number. The nucleon number is formally called mass number and is represented by the letter A, capital letter A, that's the symbol. The old name, mass number, the current name, nucleon number. The current name is better because that gives us an idea of what we are talking about. Nucleon, the number of particles in the nucleus. So we can easily remember by the name. So now what then is the nucleon number? The nucleon number, formerly called the mass number, is the total number of particles, protons and neutrons, in the nucleus of an atom. the total number of particles, the protons and neutrons you can find in the nucleus of an atom is called the nucleon number. Then the next one we want to look at is the proton number. The proton number, as the name implies, that's the current name, that's the new name. The old name is atomic number. The current name is the proton number. The current name is better because it tells actually what we are looking at. When we say proton number, we're looking at the total number of protons in the nucleus of an atom. The total number of protons in the nucleus of an atom. That's why you call it proton number. So by the time we say nucleon number, you'll be thinking about all the particles, protons and neutrons in the nucleus. And by the time we say proton number, you're looking at the total number of protons in that atom. Now, this is the nucleus, made up of protons and neutrons. Now, I can break up that atom, and then I have the number of protons, which I can now count, and the number of neutrons. So now you have the mass of an atom when they're together, and then you have the mass of an atom when they're separated. The blue ones are the neutrons, while these ones are the protons. So therefore, the number of neutrons you have inside an atom will be the total number in the nucleus, or the nucleon number A, minus the number of protons. So that will give us that. Please, this formula is very important. Always remember that. That's the number of neutrons you can find in the nucleus. This is very important in our dealing with nuclear energy. So we now come to the radioactivity. Now we're going to examine. The first thing we're going to look at is the nuclide. What actually is the nuclide? The nuclide, or a nuclide, is an atom whose proton numbers and nucleon numbers are given. So if we have an atom that we know the proton numbers, we know the nucleon number, that an atom can be referred as a nuclide. Look at an example of a nuclide, hydrogen. What do you see about hydrogen? You have the proton number is 1, the nucleon number is 1. That means there's no proton in this hydrogen. Then you have oxygen. It's another nuclide we want to look at, oxygen. For oxygen, so you have the nucleon number is 16, and then the proton number is 8. That means the number of neutrons there should be 16 minus 8. If you're giving us small n, the number of neutrons. Then we now look at isotopes. Isotopes. What then are isotopes? Because they are very important. Isotopes are nuclides of the same element that have the same number of protons but different neutrons. An isotope, like I said, you can see it on the screen now, are what? Nuclides of the same element having the same number of protons but different neutron numbers. So look at examples of the isotopes. You have deuterium. The deuterium is an isotope of hydrogen, but here you are having a nucleon number is 2 and the proton number is 1. So you see that they have the same proton number but different nucleon number. That means here there's no neutron. Here you have 1 neutron. Then you have tritium. Tritium is an isotope of hydrogen also, with nucleon number 3 and proton number 1. That means in this particular isotope of hydrogen, you have 2 neutrons and 1 proton, making a total of nucleon number of 3. Then also you have chlorine. It's also a good example of isotope. There are so many we cannot even list all of them here. But you can look at your chemistry textbooks, you can get more. So now you have chlorine 35 and 17. And then you also have chlorine 17 and also 37. So here you have the same proton number but different nucleon number. The same proton number but different number of neutrons. So because the proton number determines the characteristics of an element, that means isotopes should have the same chemical properties. They have the same chemical properties. So now, having seen that, then we are now going to look at the next one, isobars. Then isobars is just an opposite of isotopes. What then are isobars? Isobars are nuclides of different elements that have the same nucleon number but different proton number. That's why I said it's just the direct opposite of the first one. The first one is that nucleon number varies, proton number the same. In isobars, the proton number varies, the nucleon number the same. These are a good examples of isobars. So now, what do you notice about isobars? Since the proton number varies, therefore the chemical properties will also vary. That means here we are dealing with different elements. Look at carbon-14, which is carbon-14, 6. And look at nitrogen. And nitrogen is also 14, but the proton number is now 7. The nucleon number is the same, or the mass number, but the proton number varies. And the number of neutrons also varies. So therefore, this element, carbon-14 and nitrogen-14, are called isobars. They are different elements, but have the same nucleon number. Then we move to the next slide for the continuation of our discussion. Remember, we're still looking at radioactivity. Then the question is, what is radioactivity? It's very important we look at this. Radioactivity is the spontaneous disintegration or decay of a radioactive nuclide. It's a spontaneous decay of radioactive nuclide. Look at the word I want you to look at carefully. Number one is the spontaneous. What do we mean by spontaneous? It means an element that will disintegrate, element that will break down or break up, element that will decay on its own. No physical thing, no chemical thing, not weather, not temperature, not pressure. Nothing induces radioactive decay. It's just spontaneous on its own, it happens. Now, another thing you see in this definition is that is a radioactive nuclide with emission. So when the radioactive nuclide decay, it's going to give us some radiations and particles. These are called radioactive emission or radioactive radiation. What are they? Number one, alpha particle. Number two, beta particle. Number three, gamma radiations. These are the radioactive radiations. Let me say radiation and particles that are emitted. Then we'll now look at radioactive elements. Of course, we know that not all elements undergo radioactive decay. Some elements undergo radioactive decay. Most elements do not undergo radioactive decay. So therefore, elements that undergo radioactive decay on their own are called radioactive elements. On their own, they disintegrate. One thing we know about such elements is that their nuclei are usually heavy, big in size. In fact, I think the proton number should be greater than 82. Now, if only the proton number is 82, then the number of particles we have here are many. So therefore, for such heavy nuclides, they are usually radioactive elements and will tend to undergo radioactive decay on their own. So radioactive elements are usually heavy, as I said. Because they are heavy, the next thing you see about them is they are unstable. So because they are heavy and unstable, they will tend to break down until they achieve stability. So now look at this. Now, when this breaks down, it's going to become excited. That's the vibration you are seeing here. Then it's going to eject particles. The first particle ejected here is what? A proton. And then this one is an electron. And then it gives another particle, proton. Sometimes it may be alpha particle. Sometimes it may be heavier particles. That are used as these three basic particles we have in an atom does not mean that these are the only one that can be ejected. So now, also energy is given out during radioactive decay. So when a radioactive element disintegrates or decays, they usually emit three basic particles or radiations. You have alpha particle, beta particle, and gamma radiation. Now we'll now look at radioactive radiation. We already see that the ejection, the emission from the unstable and heavy nuclide are called radioactive radiations. And we say that there are three things we look at there: alpha particle, beta particle, and gamma radiations. Now, what then are radiations? Of course, you should know what we mean by radiation without talking much about that. Alpha and beta particles, along with gamma rays emitted, are called radioactive radiation. We call them radioactive radiation. So now, in these radioactive radiations, we have some properties that they are known for. And these properties, we are going to study them under some headings. So now, please like this video. So now, we are going to study them under the following heading we are going to see now. The properties of radioactive radiations can be studied or treated under the following subheadings. What are those subheadings we are going to be using to study them? Number one is the effect of electric and magnetic fields on these radiations. The effect of electric and magnetic field on this radiation. Number two, the ability of this radiation to penetrate matter, to pass through some materials. Then number three, the ability of this radiation to actually ionize gases around them. Ionization means being able to knock out particles or electrons from such gases. Now, we are going to study the properties of this radiation under these three basic headings. Now, let's start with the first one, the effect of electric field on these radiations. When I say this radiation, you should understand what we mean. Those three radiations we have mentioned: alpha particle, beta particle, and gamma radiation. Now, we bring up our apparatus. Here were evacuated glass, that's the blue circle, and then you have the positive plate, and then you have negative plate, and then you have the source of radioactive radiation. So you have the vacuum here, then you have the negative plate here, and then you have the positive plate here, and then you have the radioactive source in this place. So now we have the radioactive source. That means this particular nucleus will be able to emit these radiations that we are talking about. Now let's see what is going to happen. Let's study the first emission, and then let's examine the properties of that first emission. Now, what do you notice about the blue line? The blue line is a radiation that is deflected towards the negative plate. If you look at the deflection, it's slight, not very strong, slight deflection, and then it bends towards the negative plate. What does that suggest? Remember, in the study of electric charges, we say like charges repel, unlike charges do what? Attract. Here you have attraction between this radiation or particle and the negative plate, meaning that this radiation should be a positively charged particle. That this deflection is light means it's a heavy particle. Now let's look at the other one. So as I mentioned already, you have already seen it already. Then look at the red one. What do you notice? The deflection is more pronounced than the first one. It's a very strong deflection towards the positive plate, meaning that this particular radiation should have an opposite charges to the positive plate, and then it should be a negatively charged particle. So now, the strong deflection means it's a very light particle. It's a very light particle. Now let's look at the third one. Can you see what is happening in the third one? It's neither deflected to the right or to the left. It just passed through. And that means the electric field and magnetic field has no influence on this particular radiation. So this particular radiation is not a particle like the blue one. It's not a particle like the red one. Rather, it's an electromagnetic radiation. Rather, it's an electromagnetic radiation. Please subscribe. So now we're going to look at the next one. The ability of these radiations to penetrate matter, pass through materials. That's what you call the penetrating power of this radiation. Now, how strong are they? Are they powerful enough to pass through some materials? Can we study together? Then I have my radioactive source. Now I have the reductive source. Now let's see what is going to happen. Now, can you see? What do you notice here? Alpha particles are absorbed easily by what? A thin paper. Cut them off, absorb them. And that means a thin paper can easily stop alpha particles, showing that the penetrating power is very low. Now let's look at the next one. This is a alpha particle. Now let's see what is going to happen. Oh, sorry, that is beta particle. Let's see what is going to happen. So now what happened? What do you notice here? A thin aluminum paper was able to do what? Absorb alpha particle. Now, let's now look at the next one, gamma radiation. So now, gamma radiation, alpha particle, as I say, is absorbed by a thin aluminum paper, aluminum sheet. Now, gamma radiation now, and then let's see what absorbs it. What is that? Gamma rays are easily absorbed by what? A thick lead material. Absorb gamma radiation. So now, if I may ask you now, if you are asked to arrange these radiations according to the increasing power of penetrating power, how will you arrange them? Which has the lowest penetrating power? Alpha particle, followed by beta particle. The highest is what? Gamma radiation. In the decreasing order, it should be gamma first, beta second, and alpha particle third. Please take note of that. Remember to share the link of this video with your friends. Now we're going to look at the next one, the ionizing power of this radiation. Now, under the ionization or the ionizing power, let's examine what is going to happen. The first one, let's see what happens to alpha particle if we put a photographic plate to take a picture of what is happening there, because naked eyes cannot see that. We'll use an electron microscope to take the picture. Now, alpha particle leaves a track. A car will leave a track. A bicycle will leave a track. A motorcycle will leave a track. You can differentiate them. Alpha particle leaves a thick track, showing their ability to ionize gases around them. Now, let's see the next one now. Beta particle. What kind of track will beta particle leave behind? Now, watch. What do you notice about this track? This track is very thin, not as thick as alpha particle. So that means the ionization ability of beta particle is not as high as that of alpha particle. The higher the mass of the particle, the greater the ionization power. Let's look at gamma radiation and see what is going to happen in the case of gamma radiation. Remember, gamma radiation is not a particle, so therefore the ionization power should be very low. So the path is loose confused, no direction, just diffuse. So it's not a particle. So it cannot easily leave a track. I just did what I did for you to see that it doesn't have any track we can identify. That means gamma radiation has the lowest what? Ionization power. Now, arranging them in their ionization power from the biggest to the lowest, alpha, beta, gamma. From lowest to the highest, gamma, beta, alpha. So now, that gives us the ionization power. Now, to summarize, we are going to see the summary of all these things we have studied concerning the properties of these radioactive radiations. Number one, we are going to look at the effect of electric and magnetic field on this radiation. Remember, I told you, when we are looking at alpha particle, I mentioned some things. I mentioned something in beta particle. I mentioned some things when we are looking at gamma radiations and also others. So now, what do you notice about alpha particles? Alpha particles are deflected towards the negative plate, telling you that they are what? Positively charged particles. So now, you notice that their effect deflected towards the negative plate. What a beta particle? Deflected towards the positive plate. If you go back to that animation, you can see it clearly. What of gamma radiation? In that first animation, what do you notice about gamma radiation? Not deflected. Now, we look at the next one. Effect of magnetic field, just like electric field. Alpha particle is deflected towards the south pole. Beta particle towards the north pole, not deflected. Then the next one we're looking at, the nature of the charge. when we talk about the nature, is it a positive charge or negative or neutral? Now, from our discussion, this is deflected towards a negative plate, meaning it should be what now? A positively charged particle. This is deflected towards the positive plate, meaning that the nature should be what? A negatively charged particle. This one is not deflected at all, meaning it is what? Neutral. It is not a charged particle. It's electromagnetic wave. Then the size of particle. If you look at the deflection when we are discussing, you see that alpha particle is slightly deflected, beta particle is strongly deflected. That tells you the size of the particle. Alpha particle should be a heavy particle because of slight deflection. Beta particle should be a light particle because of strong deflection. This is not a particle. If it's not a particle, what is it then? It's an electromagnetic radiation. Then the next one, momentum. Momentum is the ability to ionize, mass times velocity. So you should be able to strike and knock out particles from gases. So now, for momentum, alpha particle should have high momentum because it's a heavy particle. Low momentum because it's what? A light particle. What do you think about this? Of course, no momentum. No momentum. So now, we go to the next one, penetrating power. Now, what do we say about penetrating power? Alpha particle is low, beta particle is high. This is what? Very high. The highest is a gamma radiation, can penetrate even a thick lead. You require concrete of many meters to be able to stop gamma radiation. The penetration or the penetrating power is actually very high. Ionization power. What do we say about ionization power? Which one has the highest ionization power? Of course, alpha particle, followed by beta particle. And this one, no ionization power because the track is confused. And then finally, the nature of radiation. What should be the nature of radiation? Well, alpha particle is nothing but a helium nucleus, while beta particle is nothing but high energy or fast moving electrons. And then electromagnetic gamma rays is what? Nothing but an electromagnetic radiations. So now, that brings us to the end of this presentation. Please subscribe, like the video, share the link of this video with your friends, and then click for notification so that when the next video is released, you will be alerted. Thank you for watching.